What do a computer geek and a body piercer enthusiast have in common? It turns out they are both big fans of an obscure metal named niobium. Niobium isn't as famous as gold or iron, but this silvery grey element has won over NASA engineers and the two parlors alike. Welcome to Cube Chemistry, where we'll discuss all the elements of the periodic table and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, if you want to influence next week's element, make sure to fill in the poll in the post section of the channel. So what we have here in the cube, it has a silvery grey color, but with a few brown patches in it. It has a lustrous reflective surface with visible striations or grain lines that are typical of a fractured or machined surface. The metal appears solid and crystalline with some irregular broken looking fragments. What we have in this cube is niobium, and after last week's episode you're probably wondering, can you lick it? So here we will use this other version of the periodic table again, which will tell us whether an element can be licked or not. We got 4 options. Sure, go for it. Maybe not the best idea. Please don't do that. And see you on the other side. Now for niobium the answer would be, sure, go ahead. Now I would like to emphasize that it is not a smart idea to just go about and lick stuff like this, and I wouldn't even do it myself. Also, let's check this periodic table and what it's saying and see if there is any nuance to it. Now, a little research will show us that niobium is considered non-toxic and biocompatible. Licking it briefly won't harm you, assuming it's clean and not contaminated with other substances. Now, if you're silly enough to actually lick it, keep these things in mind. Metals can collect oil, dust, or residues from handling or manufacturing. Unless it's been cleaned thoroughly, you don't know what's on the surface. Now, some niobium samples, like this one in the cube, have jagged or sharp pieces that could cut your tongue or lips. Now, even though niobium is safe, the material isn't produced or cleaned to food contact standards, unless explicitly made for that purpose, like medical grade parts. So at all times, be careful, and again, I would not recommend to actually do this. Now, if you want some niobium in a cube, click on the link in the description and use the promo code. You will get a 10% discount and you will also be helping out our channel. Niobium's tale goes back to the early 19th century. In 1801, an English chemist named Charles Hatchett was investigating a strange black mineral that had been sent over from Connecticut in the United States. It was named Columbium. Hatchett discovered that this mineral contained a new element. He decided to name the newfound metal Columbium, after Columbia, a poetic name for America. A patriotic nod, right? Little did he know that the naming debates had only just begun. Now at first, Hatchett's Columbium was thought to be basically the same as another element called tantalum. Now, tantalum has been discovered around the same time, and chemists found these materials so similar that it was super confusing. Now in 1809, another British chemist, William Hyde Wollaston, who was looking very interrupted by the painting made of him here, examined Hatchett's element and mistakenly concluded, oops, never mind, it's actually just tantalum. So for a while, people thought Hatchett's discovery wasn't new at all. But in 1846, Heinrich Rose, a German chemist, took a closer look at some tantalum ores and said, hold on, there are actually 2 distinct elements in here. Rose claimed he had found 2 new elements mixed with tantalum. Now he named niobium and pylopium, drawing from Greek mythology. Tantalum was named after Tantalus, a mythical king doomed to eternal frustration. So Rose named the supposed new elements after Tantalus' children. Niobe, a daughter, and Pelops, a son. Now it's pretty clear that niobium gets its name from Niobe. Pylopium, however, as it turns out, was a false alarm. There was no separate element there. Chemistry can be very, very tricky. But Niobe's name stuck to the real element that had been hiding in tantalum's shadow. Now for a while, chemists weren't entirely sure if Hatchett's Columbium and Rose's niobium were the same thing, or different. For decades, scientists wrestled with the mystery of whether Columbium and tantalum were actually the same element. But that all changed in the mid-1800s, thanks to careful work of chemists like Christian Blomstrand and Jean-Charles Galissard de Marignac. Now, using a method called fractional crystallization, they separated the two by dissolving their fluoride compounds in acid and repeatedly allowing them to crystallize. Because niobium and tantalum form slightly different salts, they behave just differently enough to tease apart. Now, Marignac also used precise weight measurements, analyzing the mass of their compounds and comparing their chemical behavior. Bit by bit, the evidence piled up. Columbium and niobium were the same thing, and they were absolutely not tantalum. By the 1860s, the chemistry word finally had clarity. 2 elements, not 1. So now that scientific mystery was solved, but now the problem is we have 2 names for the same element. So the drama kind of continued for a while. British and European scientists had adopted the name of niobium in honor of Niobe, but many American scientists kept right on calling it Columbium for nearly a century. Now, old habits die hard. In fact, American metallurgists liked the old name so much that it popped up in research papers and metal catalogs well in the 20th century. It wasn't until 1949 that the International Chemistry Authority officially said, enough is enough, the element's name is niobium now. Now, if you had a piece of pure niobium in your hands like we have in the cube, what would it be like? Well, first off, niobium is a metal and it looks the part. It's silvery gray with a bright metallic luster when polished, and many people say it resembles steel or platinum in appearance, though with a subtle gray hue. It's not a super heavy metal by comparison. Niobium is about as dense as silver, and if you dropped a niobium coin in the water, it would sink. It's about 8.6 times heavier than water. But it's significantly lighter than truly heavy metals like gold. This makes niobium jewelry feel comfortable and not too heavy to wear. Now, niobium is also quite strong and tough. On the Mohs hardness scale, a measure of scratch resistance, it ranks about a 6. Now, this means that niobium is harder than pure iron or pure gold, but it's softer than hardened steel. Pure niobium metal is actually very ductile. You can bend it, hammer it, roll it into a thin foil, draw it into a wire. It doesn't crack easily. Now, blacksmiths of old didn't have niobium to play with, but if they did, they would have found it quite workable. Add a few impurities, though, and niobium can stiffen up. In fact, tiny amounts of other elements can make niobium much harder, which is useful for some alloys, but we will get into that later. One of niobium's most remarkable traits is how unreactive it is with most chemicals. If you expose niobium to plain air, it doesn't rust or tarnish quickly. Now, over a long time, you might see a faint bluish oxidized tint on niobium's surface, but it takes a while. Niobium forms a very thin protective layer of oxide on its surface that prevents further oxidation, much like aluminum and titanium do. This protective skin means niobium can last a very long time without corroding. Now, how about acids? Well, acids are usually the bane of metals. Powerful acids like hydrochloric acids or even dreaded aqua regia, a mix of acids, can dissolve gold. Will eat through many materials, but niobium is impressively corrosion resistant. It can sit in hot, strong acids like hydrochloric or sulfuric acids, even many nitric or phosphoric acid solutions, and not much will happen. Now, aqua regia, which dissolves gold and platinum, basically has no effect on niobium metal. Now, that's a big deal because it tells us that niobium is very chemically stable. There are a few chemicals that will attack it. For instance, hydrofluoric acid can corrode niobium, and very hot concentrated sulfuric acid can too. But overall, niobium is a champion of corrosion resistance. Now, it also resists attacks by most bases and doesn't mind salt water. This inertness is part of why niobium is great for both high-tech uses and for putting it in our bodies. Speaking of body-friendly, niobium doesn't react with body fluids at all. Put niobium inside a person, say as a surgical implant or piercing, and it won't corrode or leach nasty ions. Your immune system pretty much ignores it. This property is described as being biocompatible or hypoallergenic. Now, for context, a lot of people are allergic to nickel, a common metal in jewelry. But niobium contains absolutely no nickel and causes virtually no allergic responses. It's as gentle as metals come. Now, if you chill niobium down to extremely low temperatures, we're talking cryogenic cold, just a few degrees above absolute zero, around minus 264 Celsius, niobium becomes a superconductor. In its superconducting state, niobium can conduct electricity with zero electrical resistance. That's right, zero. And it will expel magnetic fields, a very sci-fi kind of behavior. In fact, among all pure elements, niobium is one of the highest superconducting critical temperatures, about 9 Kelvin, which is minus 264 degrees Celsius. Now, this basically means that niobium is easier to get into that magical superconducting state than most other elemental metals. Only a few others, like vanadium or technetium, can do similar tricks, and they need to be just as cold or colder. This superconducting ability is incredibly useful. We'll soon see how Geeks put that to work in real life. So chemically, niobium is almost noble, stubbornly unreactive, and physically it's strong, shiny, and even a bit superconducting at low temperatures. In the periodic table, niobium sits in the middle of the transition metals, right above its old partner, tantalum, and next to elements like zirconium and molybdenum. It's not one of the more common everyday elements we hear about, but it holds its own special spot in the table of elements and in material science. Alright, so now we know what niobium is like, but where can we find it? Niobium isn't something you'll stumble across as pure nugget in nature. It loves to hang around in minerals. Typically, niobium is found with other elements, often in the same ore as tantalum. One of the primary niobium-bearing minerals is even named after Columbium. It's called columbite, which is a ore of niobium and tantalum with iron and manganese. Another important mineral is tantalite. Often the two form a mixed ore, creatively dubbed columbite tantalite. You might have heard the term coltan, especially in the context of mining in Africa. That's short for columbite tantalite. There is also pyrochlore, a mineral that is currently the major commercial source of niobium. Pyrochlore is a somewhat complex oxide mineral that contains niobium along with calcium and sometimes other elements like rare earths. In terms of abundance, niobium isn't rare in the Earth's crust. It's estimated to be the 33rd most abundant element, about 20 parts per million in the average rocks. That's roughly comparable to elements like lithium or lead in the crust's abundance. However, having niobium spread out everywhere in tiny amounts doesn't help much. We need concentrated deposits to mine. Geologists have found that niobium tends to concentrate in certain types of rocks. For example, special igneous rocks called carbonatites, which are rich in carbonates, often host pyrochlore with lots of niobium. The world's biggest niobium deposits were discovered in the 1950s, and they are quite geographically limited. Brazil is the powerhouse of niobium production by far. In Brazil, there's a huge deposit at the Araxá in the state of Minas Gerais. Brazil mines on the order of 85 to 90% of niobium. Now, if you imagine all niobium in high-tech use around the globe, most of it started as rocks dug out of the ground in Brazil. Brazil's reserves are also enormous, so they have kind of like a niobium monopoly in practice. Another notable producer is Canada. Specifically, the Niobium mine in Quebec has been a steady source of niobium, usually around 5 to 10% of the world production. Now, because so much niobium comes from one country and essentially one main company in Brazil, there's sometimes talk about supply risk. Imagine if something disrupted those Brazilian mines. The world's supplies of niobium for all our various uses could be in trouble. Now, it's an interesting example of how certain high-tech materials rely on very specific sources. However, so far Brazil has been a reliable supplier and niobium hasn't faced major shortages. In fact, some niobium prices have historically been relatively stable, partly because that one big supplier can meet demand and scale as needed. Now, once niobium ore is mined, let's say we have a bunch of pyrochlore concentrate from a Brazilian mine, how do we turn that rock into usable niobium metal or compounds? Well, the process is a bit complex and highly chemical. First, the niobium and tantalum need to be separated from other minerals and from each other. Typically, the ore concentrate is digested in acids. One crucial acid in niobium processing is hydrofluoric acid. Niobium and tantalum both form soluble fluoride compounds. Now, by clever chemical dances, for instance, adding potassium fluoride, adjusting temperature, or using organic solvents, refiners can get niobium to precipitate or dissolve, while tantalum does the opposite, effectively separating the two. This step yields niobium in the form of niobium oxide or various niobium fluoride complexes. Now, once we have niobium in purified compound form, we have to reduce it to a metal. Now, there are a few ways to do this. One method is to react niobium compounds with sodium metal, a chemical reduction that pulls the oxygen off and leaves behind a metallic niobium, kind of like stealing oxygen. Another method is electrolysis, a molten salt containing niobium, basically zapping it with electricity to plate out the niobium metal. But the most common industrial method, especially to make lots of niobium for alloying, is the aluminothermic reaction. This is a spectacular process where a mixture of niobium oxide and iron oxide is blended with aluminum powder. When ignited, the aluminum fiercely reacts with those oxides. Aluminum grabs the oxygen to form aluminum oxide, essentially slag, and free niobium and iron are left behind, melted by the heat of the reaction. Now, the result is an iron-niobium alloy called ferroniobium. Ferroniobium typically contains about 60 to 70% niobium, while the rest being iron and maybe a few other impurities. Why make an alloy instead of pure niobium? Because ferroniobium can easily be added to steel in steel-making processes. It mixes in uniformly, delivering niobium into the steel. Pure niobium metal is actually a bit more finicky to produce and handle. So far, the largest application, steelmaking, ferroniobium is the go-to product from the niobium mines. Now, if you drive a car or take a train or live in a modern city, niobium has likely touched your life through steel. The vast majority of niobium, upwards of 80 to 90% of niobium produced, ends up in various steels. Now, niobium is what we call a microalloying element in steelmaking. That means that we add just a sprinkle of niobium, often around 0.03% or 0.1% into steel, and it has disproportionately big effects on the steel's properties. It is like adding a pinch of powerful spice to a recipe. That tiny dash of niobium makes steel stronger, tougher, and more wear-resistant. How? On the microscopic level, niobium steel tends to form very fine carbide and nitride particles, like NBC and NBN. Now, these particles pin the grain structure of steel, keeping the grains small and preventing them from growing during heat treatment. Smaller grains mean tougher, stronger steel. Niobium helps to lock up the carbon and nitrogen, which can otherwise make steel brittle if they form the wrong compounds. The result, steel that's both strong and ductile, and often more weldable too. Now, the niobium-enhanced steel is used in things like natural gas pipelines, for example. Pipeline steel needs to be super strong to handle high pressure, but also flexible enough to bend over terrain and not crack. A perfect job for niobium-strengthened, high-strength, low-alloy steel. Automobile manufacturers also use niobium alloyed steel for parts of car frames and wheels, achieving high strength without adding much weight. Now, you wouldn't know by looking, but the frame of a car you drive might owe its crashworthiness in part to niobium. Even some skyscraper construction steels include niobium to reach great strength for supporting huge loads. And fun fact, some specialty knife steels include a few percent niobium to improve edge retention by forming super hard niobium carbides. So niobium can help you keep your blade sharp. Now, steel is niobium's bread and butter use, but certainly not its only gig. Next up, niobium plays a pivotal role in superalloys and aerospace applications. A superalloy is kind of a metal alloy that retains strength and stability even at very high temperatures, crucial for things like jet engines and rocket engines. Now, many superalloys are based on nickel, cobalt, or iron. And guess what? Niobium is often a key ingredient. In some nickel-based superalloys, niobium content can be as high as 5 to 6%. One famous example is Inconel 718, a nickel alloy that contains about 5% niobium, along with chromium, molybdenum, titanium, and aluminum. Inconel 718 and similar alloys are used to make parts for jet engines and gas turbines. Parts that must withstand extreme heat and stress. Now, the aerospace connection gets even cooler. Niobium alloys have been used in the space program going back to the 1960s. During the space race, engineers needed materials for rocket engines that could survive searing temperatures. They developed niobium-based alloys for this. One notable alloy is called C103, which is about 89% niobium, 10% hafnium, and a little titanium. C103 niobium alloy was used for the Apollo lunar module, specifically the descent engine nozzle that helped land astronauts on the moon was made of niobium alloy. Imagine that, a niobium nozzle roaring as Neil Armstrong and Buzz Aldrin touched down on the lunar surface. Niobium literally helped take mankind to the moon. Now, it's not just for old Apollo hardware. Fast forward to today, SpaceX, the cutting-edge rocket company, also is using niobium. The nozzle of the Merlin vacuum engine, the version of the Merlin rocket engine designed to fire in outer space on the second stage of the Falcon 9 rocket, is made from a niobium alloy. Niobium's ability to handle high heat makes it great for these rocket nozzles that see blowtorch-like conditions. Now, there's a catch. Despite its high melting point, around 2470 degrees Celsius, it will oxidize if it gets too hot in air. Above 400 degrees Celsius, it starts to rapidly react with oxygen. Now, to use it in rocket engines, engineers often have to coat the niobium alloy or design the engine so that it runs fuel-rich, which creates a cooler oxygen-poor layer over the metal. But with the right engineering, niobium alloys are fantastic lightweight, high-temperature materials. They are also being eyed for hypersonic aircraft and missile components. Where few materials can tolerate the intense conditions, niobium alloys might be up for the challenge. Now, onto an application of niobium that can be truly described as mind-bending: superconducting magnets. This is where niobium makes the geeks of the world really excited, and for a good reason. As we touched on, niobium can become superconducting at very low temperatures. Now, alloyed with other elements like titanium or tin, it forms compounds that superconduct and carry tremendous electrical currents with no resistance. This property is exploited to create powerful electromagnets. For instance, MRI machines, those big medical imaging devices in hospitals, contain coils of niobium titanium wires. Now, these wires, when cooled in liquid helium to 4 Kelvin, conduct electricity flawless and generate strong magnetic fields that enable doctors to see detailed images of your internal organs. Without niobium, MRI technology as we know it would not exist. The magnets would either be too weak or too inefficient. Perhaps even more awe-inspiring, the world's largest and most powerful particle accelerator, the Large Hadron Collider, or LHC, at CERN, relies on niobium-based superconductors. The LHC has hundreds of huge superconductor magnets, nearly 1,200 of them. And each magnet is essentially a coil made from miles of niobium alloy wire. Niobium, titanium for the main magnets. Now, these magnets are chilled about 1.9 Kelvin, colder than outer space, and produce magnetic fields up to around 8 Teslas. That's extremely strong. By comparison, a typical fridge magnet is maybe about 0.01 Tesla. Niobium allows those magnets to run without electrical resistance, which is the only way to maintain such intense magnetic fields continuously without the coils overheating. In fact, it's said that the LHC used in the order of 600 tons of niobium titanium alloys in its wiring. That's a lot of niobium doing some seriously advanced work helping scientists probe the fundamental structure of matter. Niobium's contributions don't end there. It finds its way into a range of other modern technologies too. Let's hit a few quickly. Electronics and optics. A compound called lithium niobate is a crystal used in many telecommunication devices. It has special properties. It's ferroelectric and piezoelectric, which make it great for things like mobile phone signal filters, optical modulators in fiber optic networks, and surface acoustic wave devices. Every time when you make a phone call or watch a video online, there's a good chance lithium niobate chips are helping process the signal. Now, the nuclear industry also appreciates niobium. Certain high-end stainless steels and alloys used in nuclear reactors contain niobium, partly because niobium doesn't really absorb neutrons. In a reactor, you want structural materials that don't become radioactive easily by gobbling up neutrons. Niobium is helpful in that regard. It's also very stable at high temperatures, making it useful in the harsh reactor environment. For example, the cladding of some nuclear fuel rods or components in experimental reactors have used niobium alloys. Okay, so that should satisfy the geek side of this audience. High-strength steel, rockets, magnets, electronics, you name it. Now, let's pivot to why niobium is adored by the piercers and the jewelry lovers of this world. If you ever have had your ears pierced or nose, and you ask for hypoallergenic jewelry, the piercer might have recommended niobium. Niobium has actually been used in body jewelry for decades, but it's gained popularity in recent years as more people look for safe alternatives to traditional jewelry metals. The big appeal of niobium for jewelry is that term that we used earlier, hypoallergenic. Niobium in its pure form, commercially pure niobium, is typically 99.9% niobium, does not trigger metal allergies. A lot of people have sensitivities or allergies to metals like nickel, or even traces of copper or zinc in alloys. This can cause nasty reactions, redness, itching, irritation, when they wear things like cheap earrings or certain belt buckles. Now, niobium being elemental and inert doesn't cause those problems. It's one of a small handful of metals that are so biologically inert that nearly everyone's skin is fine with it. That other famous ones are titanium and platinum. Together with niobium, these are often considered the big three safe metals for people with metal allergies. Unlike some hypoallergenic jewelry, which achieves safety by putting a coating over an allergenic metal, niobium is safe all the way through. There is no plating to wear off. For example, some jewelry might be labeled hypoallergenic, but because it's gold-plated or rhodium-plated over brass or nickel. But if that plating wears off, suddenly your skin is touching base metal and you get a rash. With niobium, the entire piece, inside and out, is just niobium, so it remains safe over time. Dermatologists and professional piercers often recommend niobium jewelry alongside titanium for people who have struggled with bad reactions to other earrings or piercings. Now, beyond safety, niobium offers something spectacular for jewelry designers. Color. Niobium can be turned in almost any color of the rainbow through a technique called anodization. This is a really neat trick. Essentially, the jeweler or manufacturer takes the niobium piece and puts it in an electrolyte bath, then applies a controlled voltage. Now, this causes niobium to form an oxide layer of a certain thickness. Depending on the thickness of transparent oxide, light will interfere with it in different ways, producing different colors. It's the same physical effect that makes a thin layer of oil on water show rainbow colors. By adjusting the voltage precisely, you can make niobium shine blue, green, purple, pink, gold, and yes, even black. Why is anodized niobium color such a big deal? Well, unlike paints or coatings, the color from anodization won't flake or peel. It's part of the metal surface itself. For example, many people love black jewelry, but a lot of black earrings or rings on the market are just black-coated steel or titanium. Now those coatings, like PVD or powder coat, can chip off eventually, exposing potential irritation metals underneath. Anodized niobium doesn't have that problem. A black niobium ring is just niobium oxide on niobium metal, all the way through. And if it scratches, it mostly stays the same color. Now, piercing shops often carry niobium seam rings and barbells in multiple colors to suit personal style. It's a fun way to have body jewelry that is both safe for sensitive skin and visually striking. And let's not forget about niobium's artistic side. Beyond just body jewelry, niobium has even been used to make commemorative coins that are real head turners. The Austrian Mint, for example, has issued a series of silver niobium 25 euro coins every year since 2003. These coins have niobium core inset in a silver ring. By anodizing the niobium core, each coin is given a different vibrant color theme. One year, the niobium center is sky blue, another year it might be purple or green, depending on the design. They featured themes from astronomy to transportation, all with gorgeous colored niobium in the middle. Now, in a world where we often have to choose between practical and beautiful, niobium stands out as both. It's practical enough to reinforce pipelines beneath the earth and powerful magnets in futuristic machines, yet beautiful enough to adorn our bodies in every color of the rainbow. From the depths of mythology to the heights of technology, niobium has made an incredible journey. So next time you marvel at the cutting-edge scientific instruments or admire a piece of shiny body art, take a moment to remember niobium, the unsung metal hero that geeks and piercers can agree on. Now, if you think we missed anything, leave it in the comments, and if you want to see another beautiful element, make sure to watch this video on bismuth next. Also, if you like this video, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode.